races the red plane. And the description in the program book is, ever since the Apollo moon landings, it always seemed that Mars was the next target for human space exploration. It's been 41 years and we still haven't been there. As the debate over a human mission to Mars continues, we ask the questions, should we go? What is stopping us? What do we need to do and consider to make a human mission to the red planet a success? I'd like to have the panelists introduce themselves. I'm sure you all know.
Kim Stanley Robinson, your guest of honor, science fiction writer, and future Martian.
I'm David Levine, science fiction short story writer, Hugo winner, and in January I spent 2 weeks at a simulated Mars base in Utah, and I'll be giving a slideshow about that right after this.
Jim Benford, former science fiction writer, recovered for science fiction writer, and my expertise is in the area of space propulsion. I'm a physicist.
So should we send people to Mars? If so, when and how? I'll start.
Yes.
Having done the simulated Mars mission, and part of the things that they do at the Mars base in Utah is they have the annual rover trials, the rover challenge, which is engineering students from all over the country, all over the world, build Mars rovers and bring them and attempt to perform certain tasks. And one of the things that we learned from that, and looking at what Spirit and Opportunity are doing right now, is that rovers are very effective at doing science, but they're not as efficient as human beings. A rover, I think the two rovers together have done something in the vicinity of 14 miles in the 5 years that they've been there. They haven't really covered a lot of territory because they have to watch every step, and there's that 30-minute each way time lag in commanding them. So you can get a lot done with a rover, but they don't deal well with unexpected situations. People are much better at dealing with unexpected situations and adapting themselves to the terrain. A human being on foot, even in a spacesuit, can cover a lot more territory and look a lot more carefully at a lot more stuff than a rover can. So I think human beings, if we can send human beings to Mars, we will get more science done in less time. The question is it worth the expense, which is indubitably much higher?
Well, there are other questions like, is it sustainable? I look at the Mars question first by saying Mars is hard. It's really hard. It's much harder than the moon. It's the typical Mars mission. I think we ought to stop thinking in terms of missions before about expeditions and settlements. But Mars mission would be 100 times longer than the Apollo missions. And it's 100 times further away. Mars is hard because it's hard to get there, it's hard to get back. It's cold, it's dusty, there's not much solar energy, there's at least a bit of gravity, 38% of Earth, but it's a tough environment to make it in. The dust alone is tricky because fine dust can get into everything, including all of your orifices, but also all of your equipment and all your lubricants and everything you want to make rotate and work. Every circuit you've got, you're going to have dust all over the place, and it's a really serious contaminant. And of course, the worst contamination is to your lungs. That's true of the moon too. So that's one of the reasons given for trying to do something on the moon before Mars. But it's hard also logistically because you go out there. There are some basic things you can use on Mars. There's water and there's CO2, but there's not much energy. You're going to have to take something like nuclear reactor with you or provide things. And I don't think in terms of let's go and stay a week and come home, or stay a year and come home, but rather in terms of a long-term development, because we saw that didn't work with the Apollo. It was a flash in the pan from flags and footprints, and nothing to follow on. So I would favor that we make a long-term investment in trying to understand another world, and that it would probably take the better part of a century to get it all together and do it well, to the point where a century from now how are we going to really develop Mars into something that's a continuing addition to the human family?
Yeah, I would agree with Jim on that. I wrote a novel about going to Mars, and there were many senses in which it was an allegory rather than a blueprint for action, talking about issues that are already with us here. And so when the book is understood as a plan or a blueprint, I think it's being misunderstood. Now, I like the idea of going to Mars, but it needs to be interrogated. Why are we doing it? What's it for? And then there are good reasons for going. For one thing, a human just makes a much better explorer than a robot, as David said, so that we can do a better job. And secondly, it would be inspirational in ways that are important, and also informational in ways that are important in terms of comparative paleontology, because what we learn there we can bring back to bear on global management problems here on Earth. And so for a long time now, I've been comparing it to Antarctica, so that it will function in the human culture and in human history the way Antarctica has for the last century. A site of special scientific interest, as they call it, legally, and a place where we learn stuff that's useful to the rest of us, a place that's interesting and kind of beautiful and inspirational, but not a crucial component of human history. I mean, Antarctica. And I think for the longest time, Mars will be like that, but if you take the really long view, then you get back into these scenarios of inhabitation, of terraforming, and of making a second Earth. And with that as the distant horizon of a goal in mind, then that begins to sort out what we need to do first to make that realistic. And one of the things we need to do first is to make a sustainable culture here. And so then you have to go back and say, well, how does Mars help us with that? And play from there.
Yeah. And I happen to believe that the way that Mars will really pay off for us, and it is, as you say, comparative planetology, that we know now that Mars was hospitable to life billions of years ago. As a matter of fact, Mars was probably more hospitable to life than Earth was in its early years, because Mars had, because of its smaller size and greater distance from the sun, had cooled to a habitable temperature long before Earth did. And therefore, the conditions on Mars were ripe for the origins of life long before they were on Earth. It's possible, possibly even probable, that life in the solar system originated on Mars and spread to Earth. We know that meteorites from Mars can make it to Earth. There's really good evidence that has happened in the past. And so, if life evolved on Mars before it did on Earth, then it's possible that we are descended from Martians. We do know that Mars was more habitable in the past, may even have been inhabited by some form of life in the distant past. We know that the climate of Mars changed so that it was no longer hospitable to life. I am concerned about the climate of Earth changing so that it is no longer hospitable to life. And I think that by studying what happened to our dead sister, we may be able to avoid that. We may be able to avoid that fate for ourselves. And I think that's the most compelling reason I can think of to send people to Mars as quickly as possible.
Yeah, and you bring up that life question, that by going to Mars and seeking to find remaining life, if we do it, then we've made the biggest discovery in human history, arguably, and also then we can run a test to see whether it's truly alien and an independent start to life, or whether it's simply a cousin and was bounced there from here, or we bounced here from there. And that, being able to investigate that question would be the greatest data point we can get in these few centuries as to whether there's life in the universe, unless suddenly a message comes beaming in and we end the Fermi paradox. So that the interest is extreme, because if we find that there's an independent start to life on Mars, then you've got to conclude that anytime there's the right combination of water, heat, and minerals, that it's going to spring up, and so life is everywhere in the universe. If it's a cousin of ours, then it's an ambiguous result, and we don't really know what it can. But nevertheless, very much worth pursuing.
Science is sloppy. You look at the experiments on Viking that were designed to definitively answer the question of life on Mars, and of course the answers that they gave were ambiguous. And so I think that's one reason we should send people, because if we send people, then you can take those ambiguous results and work with them. But still, we're not going to get the answers we expect until we get some more questions. I mean, we need to accelerate this process and really get out there and move more quickly to get that second data point, that binocular vision that helps us understand life on Earth.
Well, now speaking of life on Mars or potential life on Mars, maybe you guys can tell us more about these recent methane findings.
Yes, it's apparently not widely known, but those of us who follow these things, it's been quite interesting. In the last few years, there's an increasing accumulation of evidence, both from Mars orbiters looking at the atmosphere and from telescopes here on Earth, that there exists a residual small amount of methane in certain regions of Mars in the atmosphere. It has these characteristics. It's near around the equator, that is the warmest and lowest altitude regions. It may be seasonal, so that it's the data points are not narrow enough to convince you of that, but it might be seasonal. And that it's persistent. That is, it wasn't just a single event and it went away or so. Now, the reason you think about persistence is this. The life of methane in the Martian atmosphere is quite short. It's consumed in chemical reactions. A few hundred years it's gone. Therefore, you have to look at the sources and say, what sources could be around right now that would provide methane? The first thing to think about is volcanism. But we have no evidence for volcanism on Mars for geological timescales. What's more, the volcanism that was on Mars is in the high altitude Olympus Mons and other volcanic areas, and that's not where the methane is. So it seems unlikely, increasingly unlikely, that it's methane that's seeping up from some old volcanic activity that's hundreds of millions of years in the past, and gradually finding its way to the surface and then being dissipated in small amounts, but measurable amounts, and that's interesting that you can measure it from Earth now. So if it's not volcanism, that seems unconvincing, then it could have been brought in, say, on a cometary impact recently, last century ago or so, and it's diffused into the atmosphere. Now, that doesn't explain why it would just be around an equatorial belt. And there's no impact crater that says that. So it doesn't look like a comet either. So then there's the third option. It could be small microorganisms underneath the surface which produce methane as a byproduct of its metabolism, as do most things on Earth, including ourselves, but also including cows and bacteria and rice crops and many other places in the ecosystem. So methane is not an indicator of life per se. After all, there's methane in the outer solar system in frozen form. But the fact that it's appearing in gaseous form when it should be going away real fast if it were brought in by a comet. And it shouldn't be there still if it were volcanic. And that it's not where volcanic activity takes place. It means there's really only one-third conclusion now, and it's not nailed down, and because it has great implications, people are not willing to make the conclusion yet that we've really seen some evidence that there's something living below the surface. But boy, it's getting tantalizing, because at first the general opinion was, this is a way, the sigma bars are big on this, it's uncertain. Let's just wait and see what happens. Well, it's now too late to say that it's too early to tell. It's now starting to look like there really is something there. And so there is an orbiter that's going up in a couple of years that's going to be able to look very sensitively at the atmosphere and measure the distribution very carefully and find whether or not there are the things you'd expect to see. You'd expect to see hot spots, places where it's venting. And then you've really got a target. and you've got someplace to go and explore.
The frustrating thing about Mars is that it's so far away. Because of orbital mechanics, you can only send a mission to Mars about every 26 months. So when you start to get an interesting result like this, now you have to design and build and send up a spacecraft to investigate this interesting data point. And it means that it may take you a couple of years to get the spacecraft funded and designed and built. And then you have to wait up to 26 months for the next launch window. And then it takes something like 200 days to get there before you begin getting results back. So that's why I think that's part of the reason why it's been 41 years since the moon landing and we still aren't on Mars, because the development cycle for Mars is so extended. It's 5-10 years before. If you have an idea, it'll be 5 or 10 years before you get a result back. And then the results that you get back from something like Viking raise more questions, and you have to design and build entirely new probes in order to find the answers to those questions.
And speaking of this methane finding and the potential of life on Mars, I want to just report to people the opinion of Chris McKay, who is the NASA planetary scientist, who's always been my main go-to guide when it comes to understanding Mars and the rest of the solar system. Tremendously helpful and intelligent scientist. And here's what he was saying that he thinks is problematical, is that he regards life as at least partly a tectonic activity, that Mars, without any tectonic activity to roll over the landscape, has been essentially stable for about 2 billion years. And I'm only reporting Chris here and not my own ideas, since I don't have ideas in this regard. But that life, the average lifetime for a species is more like 10 million years. And so there's a discrepancy here that once the Mars froze out and stopped any tectonic activity way early on, then the surface was sterilized, the atmosphere went away, it froze out, connected to the ground, and so we have the Mars we have now. If there had been early life on Mars, which he regards as very likely, as David said, then okay, now it's driven underground and is in refugia, one presumes, where there's enough heat left by simply the crushing weight of the planet to melt ice. So somewhere down in the regolith, you can very easily postulate little aquifers of liquid water. It's almost certainly there. And then, you got water, you got minerals, that's all you need for life to survive. But would it have not gone extinct in the 2 billion years since then? And he thinks that even a quite robust set of bacteria, without tectonic motion to create new species, would all have, in their refuges, gone extinct over time. Died of boredom. Yeah. So, but this is a postulate, as he will quickly admit, because we don't know what bacteria in utter stability would do. Maybe it too would hit a stable cycle and just start ticking over.
Well, let me comment on that. On Earth, we don't expect new species to be produced by tectonic activity. Why? Because it's produced by natural selection, right? And it's much faster. And why shouldn't there be natural selection? It's in the subsurface as well.
I think
there is on Earth. Most of the biology of Earth is actually below the surface.
I think the assumption is that evolution is driven by change, and usually that change is some kind of change in the surrounding environment. Mars has had a fairly static environment for a long time, and so therefore we have this assumption that any life that existed billions of years ago, if it's still around, is probably still pretty much the same, because the planet itself is still pretty much the same. I love the fact that the closer we look at Mars, the more interesting it becomes. Looking at Mars through telescopes, it appears to be a boring, airless ball of rock without any interesting features. And you look closer and you see that it has a lot of interesting geological features. You look still more closely and you see that it actually has weather, it has climate, it has, looks like the impact of water even fairly recently. You look closer still and you find that it continues to be geologically active. There are interesting things happening on Mars. Mars is in motion even today. And so even though it appears static to us, I suspect we will find as we look more closely that it's more active than it appears. Everything in the universe that we've discovered, the closer you look, the more interesting it becomes, and the weirder it becomes. Everything is weird if you look at it close up and really begin to understand the peculiar processes that make it go. Even something that looks like a dead planet like Mars.
I think the pictures are very important. And to take a segue from that, the pictures we're seeing coming back from Mars, from the orbiters and the rovers, are getting to be so fascinating and beautiful that there are now photo albums of them, and there's websites to go look at them all the time. There's so many of them. And I think that is going to be a driver for people to start to see this as a real land that can be seen, it can be explored, because it's really there. It's not just a maybe place, it's a real place with all kinds of interesting features.
Yeah, we're learning that Mars is a real place. So far, up, the last 98% of human history, Mars has been practically a blank canvas on which we can present our ideas. And often Mars is a screen on which utopias can be projected, has been for hundreds of years. But now, as we are learning about the actual planet, it's becoming a real place. It's becoming as interesting as Yosemite, as fascinating in its way as the Red Center of Australia. Inhospitable, perhaps, but nonetheless alive and vibrant and strange, deeply strange.
So you did this 2 weeks in a Mars habitat simulation, and I'm thinking that must have given you a kind of Martian sympathies.
Yes, very much so. I'll be talking a lot about this in the next hours, assuming we can get the slides connected. But the thing that I learned in 2 weeks on Utah is that space travel is all about improvisation. That when you are
Like jazz.
when you are out. Well, and also, as I was talking about this with Tom Whitmore, and he pointed out that that's true of any frontier. When you are out on the frontier, when you are beyond the developed lands, you are forced to use your wits to deal with the lack of resources. You don't have a hardware store down the street. You don't have spare parts. You don't have anybody who can come and help you. So when something goes wrong, and because you're out beyond the edge of civilization, things will go wrong. Then you must make do with whatever you brought with you, or whatever you can find there. And that, I think, is what life at the frontier, life on the edge, life on Mars is going to be like every day, until we get to the point that Mars has a self-sustaining society, which as both of you suggested, is probably not going to happen anytime in the near term.
Well, no, often I've seen people get caught up in a category error of thinking that Mars is like Monument Valley, and that, it's the frontier. You go out there, suddenly something breaks, you need a crescent wrench, you fix it. But what I think the category error is that so often, if you actually were on Mars and something broke, you'd be dead, and therefore fixing it would be harder.
Yeah, that is a problem. I mean, Mars is the most hospitable place in the solar system outside of Earth. It is so hospitable that if you took one step outside of your spacecraft without a spacesuit on, you would be dead in seconds. Seconds! As opposed to the fractions of a second that would kill you any place else in the solar system. So it's extremely hospitable. It's as hospitable as a mile above the top of Mount Everest. Plants can live there. There's probably about as much sunlight year-round at the Martian equator as there is in the higher latitudes of Earth. There's plenty of carbon dioxide. There is a reasonable amount of sunlight. I believe that some Earth plants could be quite happy, even without. You probably want to put a transparent dome and pressurize the local atmosphere to make the plants survive. But apart from that, they would probably be perfectly happy with the amount of carbon dioxide and sunlight they get.
The growth rate would be pretty negligible. Basically, without much air and without much sunlight, plants just don't grow.
Well, but I think you would want to
pressurize
it.
Yeah,
you would want to pressurize it. Because for one thing, if you don't pressurize the air, it takes forever to boil a hard-boiled egg. So let's talk about getting there. Because, as I said, the problem with Mars is that it's so far away. I see you have propulsion stuff on your screen.
Yeah, I was just looking at some of the numbers. There have been a lot of proposals for how to propel things to Mars, and the first things that were thought of, and certainly the first serious proposals, were using chemical rockets. But that really doesn't make sense. It's not that you can't possibly do it that way, but it's an enormous effort because of the nature of the rocket equation and the fact that chemicals produce only a limited exhaust velocity. There are many low-thrust methods like ion rockets, which will get you there eventually. But there is a real reason to go quickly, and that's the radiation from both the galactic cosmic rays and the solar flares that come from the sun. We were lucky enough in the Apollo missions to not have one of those events during any of the missions, but you can't count on that. The frequency is enough that you're almost certain to have such a flare on the way out or back to Mars, just in a single visit. And that's really a lot of radiation. And you have to shield yourself from it, and of course water is a great shield for that sort of thing. But that's a lot of mass. But the best way to reduce the problem is to get there quickly and get out and to get down to the surface, bury yourself under the surface, and live under the surface, because you really need the protection. It's a serious hazard.
Yeah, we talk about the resources that Mars has. One of the best resources that Mars has is billions of tons of rock. Because once you're down on the surface of Mars, half the sky is now shielded from all kinds of radiation, and that'll cut your radiation danger way down. So there's a good reason to get to Mars as quickly as possible and settle in. Once you've settled in, it's a lot more hospitable than space. Even though it's almost a vacuum, it's a lot more hospitable than outer space.
Oh yeah, and regular football game, of course.
Yeah. I'd like to talk about the radiation problem. Even with chemical rockets, and we know that we can get to Mars with chemical rockets because we've sent plenty of unmanned probes. Even if it takes the full 200 and some days that a low energy transfer ellipse takes, I mean that's about the cheapest way to get there, and it takes about 9 months, 200 days. The radiation exposure from cosmic rays during that time is it raises your cancer risk by about 1%. It's like a lifetime's worth of chest X-rays in less than a year. So it is certainly an exposure that you would prefer to avoid. But on the other hand, if you're facing all of the many risks of space travel, I'd say the cosmic radiation is only a small factor. The solar flares will kill you if a solar flare should happen to hit you unprotected. But the thing is that if you're going to Mars, even if you're going on a one-way trip and you're planning on landing and never eating anything again once you get there, you still have to bring enough food and water for the trip. Now, when you bring in food and water for the trip, water is an excellent thing for blocking solar flares. So you're going to have tons of water for each astronaut, tons of water and tons of food which contains water. So if you just put that stuff around the central refuge in the ship, then you can retreat to that refuge during any solar flares. And of course, while you've been there, you'll have plenty of food and water. And even when you're near the end of the trip and most of your food and water has been consumed, well, you still have the things that food and water turns into, and those are also full of water molecules, and therefore make a great radiation shield. So it's doable. I think that the dangers of radiation, I think, are overstated.
Well, it's certainly doable. I was implying that it can be done. But the consequence of that is you're carrying a lot of mass with you. And in fact, if you're going to go out and stay in a really hostile environment for a long time, it's a big payload. You need a lot of thrust to get there. And so I think, and I think a lot of other people think that the rockets, the nuclear rockets we developed in the 60s and 70s, the Americans and the Soviets, are the right sort of answer, the nuclear thermal rocket, because it's got a lot of thrust with a high specific impulse set. We've actually demonstrated a rocket engine in the late 60s that had enough thrust to get a reasonable payload to Mars in 80 days.
Yes. Yeah. With nuclear propulsion, basically what you do is you use a nuclear reactor to heat up some kind of working fluid. I think were they use sodium?
Some use sodium, and you can use helium. You can use anything for it, actually.
Because using nuclear power, you can heat the stuff up a lot hotter than you can get with any kind of chemical reaction, which means that the velocity of the stuff shooting out the back of the ship is much higher, and therefore you can go a lot faster.
Right. A set of numbers that are interesting to me is that the Saturn V ISP, specific impulse, which is a measure of efficiency, really is 430 seconds. That's the unit we use. The nuclear, the NERVA program demonstrated 840. That's really almost twice as much. And that means you could reduce the mass of the rocket in half.
And the faster you can go, not only do you reduce the danger of radiation, but the faster you go, the less food and water you have to take along, the smaller a spacecraft you can get away with, and so the faster you can go, the cheaper the mission.
And in addition, when you get there, you're going to need nuclear power to really provide the energy you need to roll about and everything, because the power density of the sun goes inversely as the square, and therefore it's on down by a factor of the solar system, 10 or 15 from Earth. So you just really don't get much out of the solar array. So you're going to have another source of power. Nuclear is by far the most compact, per watts per pound, watts per kilogram in this country, is much better off than a nuclear reactor. They don't have to be all that big, actually. 100 kilowatts is the standard that Zubrin uses for our Mars base. I think a megawatt is ultimately what you need for settlement.
But it doesn't have to be that big.
No, it isn't that big. There's high energy density.
And the cool part about Mars is that the total land area of Mars is equivalent to the total land area of Earth, and it's completely uninhabited. So you can take your unshielded nuclear reactor and just drive it away a few miles from your base, and then you can run it and not have to worry about the indigenous population coming back and suing you. At least not for a few years. Nuclear propulsion is very exciting to me. Unfortunately, people who know more about math and physics than I do have told me that the fly in the ointment on these nuclear rockets is that all of the proposals for nuclear-powered rockets assume we can get the weight of the nuclear power plant down to something like a factor of 100 less than current nuclear power plants used on spacecraft, which one fellow referred to as styrofoam with the strength of steel.
Now, you're referring to electrical power in orbit like the Russians used, right? Yes, as opposed to another question, which is the nuclear rocket.
Right. Even on a nuclear rocket, though, the weight of the pile
it's heavy. A nuclear rocket ship is big, it's heavy, it has a big serious payload, but nobody ever said, gosh, we need to keep with the Nita Santa Maria style vehicles instead of going to these big ocean liners.
Yeah. The problem with a big spacecraft is that you can't use nuclear propulsion to launch from Earth. So that means that you have to lift all of those tons and tons of nuclear reactor up into Earth orbit.
You have to assemble in orbit.
Yeah. And that
there are
involves new technology.
There are ways to do that safely because worked out by DOE in the past. You reduce the kind of risk way down, and I don't have time to go into the details of that. I should point out there's another way to get into orbit that doesn't use chemical energy, which I personally have favored and am working on now, and that is to use beam energy propulsion to a rocket engine, which is basically like a nuclear rocket, except that the energy comes from Earth in the form of microwaves or lasers, just for launch to low Earth orbit.
So it's a
very efficient.
A microwave-powered electric rocket.
Exactly, and I'll tell you a piece of not quite news about that, and that is that the intent is that it will soon be an X Prize for directed energy propulsion into low Earth orbit with a series of stages, just like the tether prizes and the lander prizes and the spaceship and the suborbital prize that's already been won by Spaceship One. The first element of that is going to be to drive a rocket with a 1 kilogram payload at 100 meters with a source at sea level, not try to launch it, and to do it for something like 3 minutes. That's the first year's prize, and the ultimate prize is to launch something to 100 kilometers.
Now, and of course, anybody who's read Mars knows about space elevators.
Yes. Also, the solar storm, of course, is into the protective area shielded by your water supply. And, well, this is the that generation. The post-Viking out of the get-there literature had to deal with all these problems that were evident from the start. Space elevator, when I postulated it, and this also, Arthur C. Clarke and Charles Sheffield were the two that brought the attention to the science fiction community in 1978. They postulated a very, very strong material that I conceptualized as being rather thick around. A cable that was not quite as big around as this room, but maybe 10 meters across or whatnot. And now they're talking about stuff that looks like the tape inside a cassette player being enough to do it. Amazingly strong carbon nanofilaments. And a company in Seattle attempted to get a space elevator going, but wanted me to write the testimonial that the crash, the equatorial crash, would not be as bad as depicted in my book. Because now, the only thing people think when they think space elevators is it'll wrap twice around the equator and kill us all. So I'm very proud of that.
Well, as you said yesterday, the blueprint for utopia is less interesting than the thought of what would happen when it falls down.
This is the reason that movie producers, they don't want anything except for the big crash. But if it's as thin as a cassette tape, then in the fall itself it will burn up, and there will be nothing to hurt anybody. The people on it will be in trouble. But
that would be a fairly small percentage of the total population.
Yes, and then the equator itself is fine. If we are to take advantage of the solar system, then this space elevator technology will be not only have to be used, I think, unless, well, I shouldn't say that. It would be a way to do it.
Yes. Let me just throw out another thing. This is an idea that a friend of mine, Keith Lofstrom, had years ago, was published in Analog. It's called the launch loop. The launch loop is a very long chain of iron plates, which is accelerated through a linear accelerator. You may have seen it. It's a toy. It's a little thing that blows a ribbon around, and it sort of goes around like this. Imagine that, except that it's an iron chain about 1,000 miles long, and you accelerate it through a linear accelerator, so it goes like this, which means that it has enough upward momentum on the upside to hold itself up. It actually you accelerate it along the ground, and then it goes up to the top of the atmosphere, and just its incredible momentum, because it has to be going extremely fast, keeps it up. And then you hook on to the upward leg with electromagnets, and you can fling things into orbit that way.
But wait, then what about the moment of acceleration? That's like Jules Verne's cannon.
Details. It worked for Jules Verne. It can work.
Well, it has to be on physical grounds. That is, you have to have enough velocity when it loses contact with the ground that you can reach that high altitude. It's just a single cannon. It's just a connected cannon. And so all of it has to be reach that velocity. And then when it's running horizontally along the ground, which means that it's far faster than the speed of sound, which means there's enormous shock waves that dissipate energy.
Continuously.
And being on board would be very exciting.
Very exciting. Well, I think the answer to the problem of the passengers getting squished on launch is that you gradually engage the electromagnets, so it doesn't take off with a jerk. It takes off with less of a jerk. And, technical reasons. But there aren't. I mean, the space elevator was a weird idea not too very long ago, and now there's people actually looking into the technological details of making it function.
And the venture capital, too.
You may know, I'm sure some of you know, science fiction fan Jordan Kerr was a member of the team that won it wasn't an X Prize, but it was something very much like an X Prize for space elevators. They're working on the beamed power component of beaming power to the crawler that climbs this slim ribbon of cable, which, the cable itself, I think, is the hard technical challenge, but there are other people working on that. But he's working on the beam power and
the climber.
The climber, and it's actually working. So there are people who, the space elevator was a weird science fictional concept as little as 10 years ago, and now people are actually looking at how do we make it possible. It may very well be that there are other means of getting into low Earth orbit that are weird science fictional concepts, or not even weird science fictional concepts yet. We'll still be using it for 3 years. I have faith in the future. So yes, it's about 1:45, and I believe we are supposed to be out of here at 5 or 10 minutes to the hour, so we have a few minutes for questions. Wow. We'll start. Okay, start in the black up there, then you.
James Lovelock postulated that we easily find life on our planet because there seems to be out of chemical material, and Mars is famously not. So I understand that recently there have been some methane plumes detected. I just wondered if you were aware of that, and how that fits with the person.
Yeah, we were talking about methane on Mars.
Yeah, and it does stand as an out of equilibrium signature, but it's only recently discovered. It's a very small thing, but in the rest of the atmosphere is carbon dioxide. It's quite an equilibrium atmosphere, but the methane plumes look increasingly like they're driven by life. That's my opinion. And people are very reluctant to draw that conclusion because it's such a big conclusion.
Yeah. Extraordinary claims require extraordinary
Precisely.
Okay. And again,
I'd just like to mention that Lovelock, in his early book, Greening of Mars, talked about people walking around breathing an atmosphere that had 7% of the carbon dioxide. And since he is a world-famous scientist and I'm an English major, I'd just like to point out that is at least a 2 magnitude error in how much CO2 we can take without dying instantly. So maybe it was a typo. I'll give him that.
How much oxygen is in the atmosphere?
Well, a lot, like a flammable amount. It was quite a bit.
I'd like to point out that Jeff Landis, in a story in recent Asimovs, pointed out that the upper reaches of the Venusian atmosphere are actually more pleasant for human beings than even the deepest parts of the Martian atmosphere. So the green shirt, then the black shirt, and then you in the blue shirt, and then you in the green. Yeah. So you in the green shirt back there. Yeah. Should we go to Mars as a life insurance policy for the human race?
No, I hate that. That's Stephen Hawking and a kind of lunatic fringe that actually erects the larger human community's sense that this is a rational and sensible enterprise. It's not good to say if we just kill off everything on Earth that 200 people are going to restart things from scratch somewhere else. It doesn't work out in 3 or 4 different ways, and we in the science fiction community can point anybody to Joanna Russ's great novel, We Who Are About to ... as a very convincing deconstruction of that myth. And so I just think it immediately makes us look illegitimate and foolish. And it's, Hawking, we always have one great scientist on that planet, and he's it right now. But when scientists go emeritus and start talking philosophy, it often is a shambles.
Well, that's life insurance is not the only reason, of course, and I personally don't carry life insurance. It's not a good investment by any age. There's certainly lots of reasons to go to Mars and go to Mars. They have nothing to do with trashing the area. We should never imply that that's a good idea.
Yeah. I'll give you a very brief follow-up. If we do discover life on Mars, should we terraform it? There's a whole other panel on that tomorrow. Okay, I think you were next, and then you, and I'll take some more hands after that if we have time.
If we're going to be going to Mars, would the next mission be on the surface for several months at least, and they're going to be on the surface in a low gravity, so that the medical implications. So I think one of the things that's going to have to be worked on first is ways of preventing muscular and skeletal degeneration from the lower gravity. I
Yeah, talking about how any expedition to Mars would be on the surface for at least some months in lower gravity and would have to worry about muscular degeneration. The fact is, though, is we've had people on the International Space Station and on Mir for years and years, and there are problems with muscular degeneration, and I believe that any successful mission to Mars would have to provide some kind of rotational gravity for the trip. But even a third of the gravity is much more than nothing, and there may be some muscular degeneration, but we're going to be, if we actually send people to Mars, they're going to be working really hard.
And they're going to be carrying
a heavy pack.
Yeah.
So I agree. Frankly, that's the least of reasons not to go there. And one of the things that Zubrin says that I don't agree with everything he says, but one of the things that he says that I agree with is we should not be wasting our time studying the problems, studying the reasons not to go. We make progress only when we stick our necks out. We make progress by actually going and doing the things, and then we discover what the problems are and find the solutions. If we allow ourselves to be distracted by, oh, we can't go until we solve this problem, oh, we can't go until we solve that problem, then we'll never go. And that's what's happened so far, and we'd like to break that cycle. Let's see, who was next?
Alan and
yeah, you and me.
Okay, this is directed for Jim Benford. If I'll catch up with you later for a follow up, if I may. You're talking before about the power requirements for the Martian surface for outpost habitat, whatever, being in a neighbourhood of 100 kilowatts. Yeah. Is it at all feasible, being as that there are some countries who don't even like nuclear submarines parking at their harbours, let alone launching power sources on rockets, which occasionally go bang. Is any thought being given to having, say, an array of RTGs that might power a Stirling engine after you've leveraged some propellant out of the atmosphere in that?
So talking about using a Stirling engine instead of atomic power.
Yes, right. Personally, if I were going, I'd bring a reactor with me. It's fairly low maintenance. It's self-contained. It's got a lot of energy in it, and I don't have to figure out how to make something work on Mars for the first time, and I'm dead if I fail.
And it's absolutely the case that there are going to be protests about any attempt to launch an atomic reactor into space. There have been in the past, there will be in the future, and that's just one of the many problems we'll have to deal with.
Although it's been done.
Yes, it has been done. It has been protested.
Yeah, no, it's been successfully done, and we've even had a launch failure on RTG, in which the RTG survived perfectly as it's designed to. They had a mass cover around it, went right into the Atlantic, and so I'm not at all worried about it. We can do it the way the Soviets did, but the Soviets never had any safety on it.
The Topaz.
I'd like to point out that the next major NASA rover called Curiosity is going to be powered by atomic power, and also is the first rover that's capable of defending itself. It has an atomic reactor and a laser. A laser that can burn through rock. So the Mars rover have better watch now. Okay, I think you were next.
Yeah, just a technical point on the concept of using microwave power beams to power your crawler heading up the space elevator. Is that actually a technical necessity, or given how strong your space elevator has to be to hold itself up, could you basically just load whatever power supply you need on the crawler itself and not worry about microwave beaming?
Yeah, so why power the crawler with a microwave rather than just putting batteries or whatever on the crawler?
Well, you made the point already. If the space elevator cable is strong enough to withstand the orbital pull, it's strong enough to serve as a kind of railroad track. You just put something on it that has and it can work the way Swiss chariots work. That the side going down is pulling up the side that's going up.
Yeah.
A very little motor to add the extra. As I understand it, the problem is not big.
So in that scenario, it's the tensile strength of the cable that puts an upper limit on the size of the capsule, on the weight of the capsule.
Which could be quite immense. You're talking 30-story hotels. It would be really a cool tourist device.
I think a lot of the emphasis on the climber development in recent years has been how do you build the things. You're going to need climbers during the construction phase.
I think the assumption behind the use of beam power is that there's going to be other things than the strength of the cable. The ability of the climber to grip the cable and pull itself up. There's going to be a maximum amount of weight that can be supported by the grippiest gripper, and therefore every pound or kilogram of weight on the climber that is used to power the climber is a pound of payload that you don't have. So I think there's going to be something that provides an upper limit to the weight of the climber, and if that upper limit is not the strength of the cable but something else like the grip strength, then making the climber lighter by putting its power supply on the ground would be a way.
And before we disperse, I would like to lay out to the community here the claim to still be the only human being that has eaten a piece of Mars on purpose. And therefore to have Mars in my bone structure atomically and being perhaps the only true Martian on the planet, or at least the first humans who have done it. Because when I was given an SNC meteorite, and it's a necklace that my wife wears almost all the time, and gets her a lot of good comments at the U.S. Geological Survey. What's that big gravel? Oh, let me tell you the story. Well, but then it was Terry Bisson's idea, I'll admit that. But he said, Stan, you should eat it. And I did. But you gotta be first at something, right?
I can't think of anything that could possibly top that, so thank you all for coming. And stick around for the next hour. I'll be giving you slides of my vacation on Mars.
Cool.